Okay, so what we're going to do is, even though we're quizzing over covalent compounds on Wednesday, we are going to go over the next type and flip-flop our days a little bit. So the next type is called ionic compounds, and ionic compounds are where we involve a metal and a nonmetal and put them together. And so in this example, we have a picture of a person at the Bolivian salt flats, also called Salar de Uyuni, and there are these large salt flats in Bolivia where, if we look, it's just this endless plain of salt. And so, what we're going to do is kind of look at some of these compounds and different types of salts among other ionic compounds. So, as a quick recap, valence electrons. These guys are the number of electrons on the outer shell. Hopefully, you guys understand that by now. The maximum valence number is 8. And a proton has a positive charge, and an electron has a negative charge. This is really going to come into play here. And then covalent compounds involve the sharing of electrons, whereas ionic is giving and taking, or as we call, stealing of electrons. So an ionic bond is a chemical bond where electrons are stolen from one atom by another. And ionic bonds typically happen between metals and nonmetals, as I mentioned earlier. So as gaining or losing electrons throws off a 1-to-1 ratio of electrons to protons in an atom, these atoms become charged. So what do I mean by that? Well, long story short, if we have a sodium Lewis structure, sodium is in group 1 of the representative elements, meaning it has one valence electron. If this is stolen from a chlorine Lewis structure, well then now my sodium is missing an electron. Now here's the problem. Sodium, to be sodium, still has those 11 protons, but now it only has 10 electrons. This means it has a net charge of positive 1. Chlorine, on the other hand, remember that our 1-to-1 ratio of protons and electrons in a stable chlorine would be 17p and 17e. Well, now I have 18e because I just stole that electron from the sodium. Well, now, since I have one extra electron, I have a charge of -1 because electrons are negatively charged. So this is the charge here. When you have a charged atom, this is called an ion, hence the name ionic bonding. So this is the bonding between charged atoms. Phil's back. He wants you to steal. So remember that in ionic bonding, we are stealing electrons. How you doing? Cations. So when an atom has more protons than its electrons, so when it has a positive charge, it is a cation. A cheesy way to remember this are that cation has the word cat in it. Cats have paws. So cations are positive. If you never remember that I just said that, that would be perfectly a-okay. However, if you need that mnemonic device to help you remember that cations are the positive ones, don't forget that. Now, in this example where we bonded the Na to the Cl, okay, the Na is a cation because it donates an electron. It has an electron taken away from it from the chlorine. So therefore, when it's missing an electron and it has more protons than electrons, more positives and negatives, it is now a cation. So atoms that form cations are positive charged atoms after you take away an electron. Typically are in the first 4 groups of the representative elements, and we're going to do some practice later. The only exception is carbon. Carbon goes both ways. So it can be positively charged or negative, but we're not going to worry about that. Oh, here's another close-up of the Bolivian salt flats in Salar de Uyuni. Okay, so here's a picture of what's going on. If you guys forgot the 1-to-1 ratio of protons to electrons, sodium, if we have our Bohr model, has 11 protons and 11 electrons. When we take one off, this guy has been bumped off. Well, then that means that we now have one more proton than electron. So this is now a positive charge of 1. because we lost an electron. So now it's one more positive than it is negative. Remember that you can't take the protons away from an atom, otherwise you change its identity. You can only do that with electrons. Now, atoms with less protons than electrons are called anions. So when we have an atom that has one more electron than it normally does, it's got a negative charge and it's an anion. So here's a cheesy way to remember anion. If we look at the bad character in a novel, bad character, bad guy, is the antagonist. Anions are negative. Okay, negative is a synonym for bad. So if we think about that, an for anion equals negative. Helpful mnemonic device. Now, if we clean that up a little bit and we look back at our chlorine, chlorine should have 17 electrons because it has 17 protons. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Well, I skipped this one for a reason because it's not supposed to be there. However, chlorine took it from the sodium atom in our first example, so now it has 18 electrons. This guy's number 18. Since it has 17 positives and 18 negatives, it has a net charge now of -1. So now you guys see a periodic table of elements depicted on the paper that you picked up in the front of the class. Now we're going to do some examples of oxidation numbers. Oxidation numbers are just the charges that we just did. So now I'm going to clean this up a little bit. Our first one is magnesium. Magnesium, if you find it on your periodic table, is located right here. This is group 2 of the representative elements. That means that magnesium has 2 electrons it can give away. If we draw our Lewis structure for magnesium, it has 2 electrons we can get rid of. So when we get rid of 2 of them, it gives it a positive 2 charge. So anything in this group is going to have a positive 2 charge. So magnesium's oxidation number or charge is automatically going to be Mg2+. Well, now let's do another example. If we do hydrogen, which is right up here, hydrogen has 1 valence electron to give away. It's on the left side of the periodic table, which means it's going to give, it's going to be a cation. So hydrogen has 1 to give away, and so its oxidation number is 1+. So anything in this group is going to have a number of 1+. Now let's do carbon. Carbon's right over here. Well, carbon could be +4 or -4. Remember, it's the odd man out that can be either one. So in that case, carbon is going to be C, 4+ or minus. Carbon is not typically involved in ionic bonds, so you don't really have to worry about that one. I'm not going to put it on an assessment or anything like that. Bromine is a halogen, so bromine is over here. Bromine can have, now we're getting into anions, so now we got to think about this. Well, bromine has 1, 2, 3, 4, 5, 6, 7 valence electrons. Bromine wants 8. It wants that extra electron to be stable. So to have 8, it's going to take on 1 more. That means it's going to gain a charge of -1. So bromine would be -1, as well as all the halogens. So all the halogens would be -1. Lithium. Let's do lithium. Lithium is in the alkali metals, so it's right about here. So that would be lithium +1. Or we could do 1+, either way is fine. Aluminum. Aluminum is right about here, so aluminum would be Al3 plus. Oxygen is in this group. Oxygen is right here. So oxygen would be O2 minus. Krypton. Good old krypton. Krypton is a noble gas. Krypton does not have an oxidation number. The reason is because krypton does not like to bond. It has 8 electrons, so krypton has an oxidation number of 0. So those are the examples you should have filled out at the bottom of page 1. Now turn over the page. Okay, so the goal in ionic bonding is for the elements in groups 5 through 7 to achieve full octets. That means if you're towards the right of the periodic table and you're in groups 5, which would be these guys, all these guys, so 5 through 7, that means, that means you want 8 electrons, okay? Obviously, the ones in group 8 already have 8 electrons, so they don't need to meet that goal. Now, if you're in group 5, you want to get 3 electrons to get to 8. Hence, your oxidation number would be 3 minus. That's how many more you want to get to 8. If you're in oxygen, the oxygen group, you have 6 valence electrons, so you want 2 more electrons. So you want a charge of 2 minus to get to that full octet. If you're fluorine, you only need to get 1 more electron, so that means you want 1 more negative charge to get a full octet of 8 electrons. Elements in groups 1 through 3, remember, are giving the electrons. They're having them stolen from them. So that those elements in 5 through 7 can make full octets. So basically, the elements in groups 1 through 3 are kind of sacrificial lambs, okay? They're giving away electrons to the guys in 5 through 7 so they can get full octets. Okay, so we're going to do a couple practices here. How do we draw this out? So ionic bonding is actually more simple to show than covalent in that you take the cation. The cation is typically the metal in the bond. The metal is going to give away its electrons, so all you have to do is just draw an arrow showing that this electron from calcium is going to fit into that chlorine right there. Same for this guy. So all you have to do is just draw arrows. So this is how we show it. So we're going to draw a couple examples. Let's do magnesium oxide. Mg. So you start by doing the Lewis structures. Oxygen. Okay. So now I zoom into this guy. I'm going to draw an arrow from this and point it to pair up to this lone electron. So it is similar in that we're pairing electrons up. So all the lonely electrons need to have a buddy, kind of like we did in covalent bonding. This guy is going to pair up with that guy. Then we're going to draw our charges. Magnesium, I got rid of 2 electrons if I'm magnesium. So that means I am now feeling 2 more positive than I was. I got rid of 2 electrons, so I have 2 more protons than I do electrons right now, since I got rid of 2 of them. Well, this oxygen just took on 2 more negatively charged particles, so now it's feeling a little more negative. So this guy has a 2 minus. Okay? Let's do another one, AlF3. I'm going to do that on this side. Aluminum has 3 valence electrons. Fluorine, we need 3 fluorines in this, so we're going to draw our Lewis structures. Okay, here's what we do. So this guy is going to go over to this fluorine. This guy is going to go to that fluorine. There's a bad arrow, my bad. And this guy is going to go to that fluorine. So now we need to do our charges. So aluminum got rid of 3 electrons. Okay, 1, 2, 3. So since I got rid of 3 electrons, I am feeling 3 more positive than I was. This fluorine, each fluorine took on 1 extra negatively charged particle, an electron. So this guy is feeling 1 more negative. This guy is feeling 1 more negative, and so is this guy. So that's how you do the charges in bonding. The reason that these atoms bond is because of their charges. Remember, opposites attract. So in ionic bonding, these opposite charges are the reasons these compounds exist. So in your table salt, which is NaCl, okay, the positively charged sodium bonds with the negative, is attracted to the negatively charged chlorine. That's why they stick together. Same case with calcium chloride. CaCl2 is your road salt that you guys put on the roads in winter when it ices over. This is what causes the road salt to become liquid. It's because it's a salt, an ionic compound, so it lowers the freezing point of the ice, like you did in the ice cream lab, so we can drive on the roads and get to school or work. We're not going to worry about naming today, so we're going to skip that. But you guys can go to properties. So ionic compounds have high melting points. Okay? Covalent has low. So this is where they contrast. Another way to remember this is I rhymes with high, while co rhymes with low. So covalent rhymes with low, so it has low melting and low boiling point. Ionic rhymes with high. I rhymes with high, so I has high melting points and high boiling points. And then we're going to look into this when I get back, but the way they form is they form solids by alternating patterns. So sodium chloride, table salt, looks like crystals because you have a sodium atom with a chlorine atom. And then a sodium atom with a chlorine. Sodium, chlorine. And then it alternates like this, which is why it forms 3-dimensional crystals. Because if I just did that side, then I would do this side. So then it keeps bonding like that. And then it would also make a 3-dimensional cube. And so on. And they're also good conductors. So covalent compounds are not good conductors, they're poor conductors. Ionic is actually a pretty good conductor because they contain the metals. Metal's a good conductor. It conducts electricity. It conducts heat. That's why you don't touch a hot skillet when you're cooking. So as long as we have a metal involved, we're going to be a decent conductor of heat and electricity. However, they're only conductive in fresh water. So for our punchline, you need to know that an ion is a charged atom. And the difference between the cation and the anion. Okay, cat, positive. Cats have pause. Cat's positive. Anions are negatively charged. Okay, ionic has a metal involved and a non-metal. It's not metal to metal because that's something completely different called an alloy, but metal to nonmetals that's an indicator that you have an ionic bond or an ionic compound. And remember that the negative guy, the anion, so anything in groups 5 through 7, wants to have 8 electrons in its outer valence shell. So they want a full octet. Now, again, we'll do the naming process later, but you need to remember that ionic compounds are good conductors in water, only in fresh water, and they have high melting and boiling points, unlike covalent, which has low melting and boiling points. And that ionic compounds form crystal solids because of that alternating pattern that I drew just now. Hope that helps. Keep these notes for tomorrow's class, and we will continue. We'll actually review over covalent tomorrow, and then we'll assess on Wednesday, and then we'll pick back up on ionic. Thanks for listening.